Hi, good afternoon, good morning for all joining our live webinar for vacuum in freeze drying. Welcome to all of you. We are really happy to host the webinar today. Our presenter today is Carsten Ruth, our sales director here at Vacubrand. For the better quality, we have switched off the possibility of the microphones. So if you have any questions during the presentation, feel free to enter your questions into the chat. We will be very happy at the end of the presentation to answer your questions. If we cannot answer the questions, we will absolutely follow up with you later on, but please feel free to answer any questions through the chat function. And now it's time to start with the webinar. So welcome again, and please go ahead, Carsten.
Welcome to our webinar session titled Vacuum in Freeze Drying. In this session today, we will look at the background of the freeze drying process itself, focusing on the role of vacuum as a key process parameter in this gentle drying method. And from there, look at corresponding vacuum technologies applied for this application. My name is Carsten Ruth, and I'm the sales director of Vacubrand here in Germany. I'm with this company in my 20th year now, and for many years I was handling our business activities in Asia Pacific, Middle East and Africa before stepping up to into the sales director position, where I'm now leading our global sales team. My background is actually chemical engineering, so I'm very familiar with the application side of our products. Here you see today's agenda. As mentioned, we will focus on the freeze drying process and specifically the role of vacuum and vacuum technologies applied. We will start with the challenge at hand, so we will start to look at the key challenges and purpose of the freeze drying process. We will have a little bit of a look at theory and practice in this application. We look at the actual working principle, and from there guide you towards the most appropriate vacuum technology solutions applied. And of course, there's space for questions which we would try to answer to the most extent. What is freeze drying actually used for? Freeze drying is actually all around us. It's applied in specifically the food industry, and I'm sure any of you who has ever gone to a supermarket had at one time a food package in hand, and if you look on the description in the back of the package, you will sometimes see the product has been freeze dried. And this applies for spices, it applies for instant foods, it applies for coffee, juice concentrates, a wide range of applications. Furthermore, freeze drying is applied on the side of pharma and biotechnology. For example, in the research and production of vaccines, of medical products, of active pharmaceutical ingredients, and many more. Specifically in the pharma sector, freeze drying is often applied wherever the 3D molecular structure of a specific substance has to be preserved to ensure the pharmacological function of the product. And freeze drying is also applied for various kinds of heat-sensitive products. So we can summarize that freeze drying is a drying process that helps to conserve structure, function, and shape of molecules. In a freeze drying process, there are different challenges that have to be addressed. One is the process pureness. Contamination-free processes lead to contamination-free products, which is essential specifically in the food, pharma, and biotechnology area. Efficiency, of course, is a key aspect. Only efficient processes lead to sophisticated products. Reliability of the system and reproducibility of the process itself. And finally, the sustainability approach that is common everywhere nowadays. Freeze drying is a very sensitive process that helps to preserve product structure and characteristics. It's a contamination-free process that provides pure products at the end. It should be efficient. It should remove traces of moisture and solvents. Specifically on the production, but also on the research side, process reliability and reproducibility is essential. And of course, a high degree of process and user safety needs to be granted. We at Vacubrand address these requirements for decades with our state-of-the-art products. Now coming to the process of freeze drying itself. To put it in simple words, it's the way from ice to vapor and back. As freeze drying is based on the thermodynamic principle of sublimation. Sublimation is a phase transition from solid state directly to gaseous state by skipping the liquid state. So in freeze drying, there will be no intermediate melting. Let's look at a small thought experiment on this. Freeze drying, as all other drying processes, has the purpose to remove moisture and solvent. And whenever removing moisture or solvents, there are two parameters that we can play with to achieve this. One is temperature and the other is pressure. Now imagine we take a piece of solid water, ice, a simple ice cube. And we now start putting energy into this ice cube by heating it up. So we use the process parameter of temperature. Eventually, the ice cube will start melting. It becomes liquid water. And when we put more energy, we heat further, we come to the point where it starts evaporating. At the end of the day, the entire ice cube has disappeared. We can achieve the same result by keeping the temperature constant and adjusting the pressure. So we put our ice cube under fast evacuation and we reduce the pressure down to a point where the solid ice directly converts into vapor, the so-called sublimation stage. So from here, all ice is converted into vapor and the vapor escapes. In both of these experiment runs, we have achieved the same result, starting from a solid ice cube to full dryness at the end. But what we have not considered so far is the actual sample, because nobody would work with the pure drying media at all. So let's repeat our experiment and add a sensitive sample. In this case, what we do, we wrap our ice cube into a sensitive shell, a thin paper, for example. So we have a small paper cube filled with ice to start with. And again, we use our two process parameters available. At first, temperature. Our paper-wrapped ice cube is heated up. The ice inside will start melting. The paper will absorb the liquid water, and eventually, putting more temperature, the water will evaporate, And at the end of the experiment, we will have some kind of a crushed paper ball that is fully dry. But the shape has nothing to do with the initial starting point with a perfectly shaped cube. So let's repeat this experiment with the process parameter of pressure. Again, we take our paper wrapped ice cube and we fastly evacuate it down to the sublimation curve of water. From there, again, the solid ice will be converted into vapor. The vapor itself will escape through the pores of the paper and will disappear. And at the end of this experiment, what remains will be a perfectly shaped, fully dry paper cube. What do we learn from this? Well, in this experiment we see that the process of freeze drying with its background principle of sublimation has fully kept the initial structure of our sample, the paper cube. And there was no collapsing which happened before during the liquid stage of water. So much for a small thought experiment. In real life, freeze drying will start with your sample, and in the sample preparation it will be pre-frozen. In most cases this is done externally in a deep freezer. Sometimes some freeze drying units, they offer the freezing stage inside of the freeze drying unit, specifically when it comes to production scale units. So we have our pre-frozen sample that is then in the freeze dryer rapidly evacuated down to the sublimation curve of water in this case. From there, the sublimation, the transition to the vapor phase starts and the freeze drying process is proceeded. Now normally this happens, or it definitely happens, at pressure levels below the triple point of water. Because at these pressures there is no more liquid phase possible, which you can see from the diagram here. In order to proceed a safe process, of course we will not work exactly or very close to the triple point, but we keep some spare tolerance. So we will work somewhere in the range of 1 millibar and below for the main drying process. And here you see some samples that has been freeze dried. On the left side, the upper part of the picture shows peptide samples that have undergone freeze drying in a perfect way. So in their dried stage, the molecular structure has been preserved. The sample has kept its original structure. The lower part of the picture shows the result of a failed freeze drying process. These are the exact same samples, but what happened here is that during the freeze drying process, intermediate melting occurred. Maybe there was some leak in the system, maybe there was a break of the pressure leading to pressure spike, or other effects that have led to intermediate melting here. Once there's liquid water present, under the strong vacuum condition of the freeze drying system, the water will immediately start boiling. You will see bumping retardation, which leads the sample to splash all over the container. And at the end of the day, the sample is basically destroyed, and what remains, it's just a slurry that is not usable anymore. So this again shows how sensitive the freeze drying process itself is. Commonly used in freeze drying are pumps that on one hand achieve a very good vacuum power down to 10 to the power of minus 3 millibar. On wide scale, conventional rotary vane pumps, oil-sealed, oil-driven rotary vane pumps are used. But specifically for high demand processes that have specific requirements to cleanliness, to being contamination free, the latest trend is more and more towards dry technology pumps. Now looking at freeze drying, it is, as usual, the more is not always the better. To explain this further, let's again look at a small thought experiment. We have a look at 1 gram of solid ice, and we now consider how much water vapor is generated by this 1 gram of ice. And this strongly depends on the actual pressure condition in the system. So when we work at 1 millibar, the effective vapor volume that is generated by this 1 gram of ice is in the range of 1 cubic meter. If we lower the pressure by 1 order of magnitude down to 0.1 millibar, we will have an expansion factor of 10, so the resulting effective vapor volume stands at 10 cubic meter. And if we give full power to the system and go down to 10 to the power of minus 2 millibar, we will have 100 cubic meter resulting effective vapor volume. And the effective vapor volume is what has to be handled by your freeze drying system. And the smaller you keep the effective vapor volume, the more efficient your process will be. And therefore, in most cases, the freeze drying process is separated into 2 steps, 2 phases. At first, you proceed with the main drying process. That is proceeded somewhere in the range around or slightly below 1 millibar. This is far enough away from the triple point to ensure a safe process. But on the other hand, it is still in a range where you don't create too much of excessive effective vapor volume. Once the main drying process is finished, there may be still some residues of moisture that are encapsulated into particles or that are bonded with your molecules that you may want to remove to achieve your final drying rate. And this is then proceeded in the so-called final drying or residual drying step, which then requires stronger vacuum and is usually done somewhere in the range of 10 to the power of minus 2 millibar. Regarding vacuum technology, of course, you need an instrument that is capable of handling both of these process steps. So let's have a look at the actual freeze drying system, at the setup and the various process steps. A freeze dryer consists of a drying chamber, a condenser, and a vacuum source. In some cases, the drying chamber is separated from the condenser. That's a so-called 2-chamber system. And there are sometimes single-chamber systems where the drying chamber is actually positioned inside of the condenser. So you dry your samples, you place your samples actually inside of the condenser. Then there's a vacuum pump attached, but the role of the vacuum pump is simply to provide your suitable process condition. It does not really remove anything out of the system, as this is the role of the condenser. Ice condensers for freeze dryers are usually available in different versions. Sometimes they're rated at -50 to -55 degrees centigrade. Some go down to -85, and they're more suitable of dealing with organic solvent traces, for example. And for aggressive media, there are even special versions that go beyond -100 degrees centigrade. In a freeze-drying system, once the sublimation process has started, as you have seen from the previous phase diagram of water, there is no more liquid phase possible as long as you remain below the triple point with your pressure condition. And therefore, within the freeze-drying process, you can even put additional energy to your sample by heating, for example, in order to speed up your process. And this is an option for many freeze-drying systems on the market, specifically shelf dryers, where there's heating options for the shelves available. Here you see a simple chart of a freeze-drying system. You see the condenser below, the drying chamber above, a typical lab system layout, and there on the chamber itself there's the manifold for holding the sample flasks. On the side of the condenser chamber there's the vacuum connection with an isolation valve towards the pump, and then there's the vacuum line to the pump. So at first, when you start up a freeze dryer, you isolate the pump from the freeze dryer by closing the isolation valve. And then you allow approximately 30 minutes warm-up time for the pump, and at the same time you can cool down your condenser. Because only when both pump and condenser are at their respective operating temperature, the system is ready to go. Then you take your sample out of the deep freezer and you hook it onto the system. From there, you then open the valve in order to apply the vacuum to the system and achieve the fast pump down towards the sublimation curve. The pressure will be lowered, and for systems that are openly positioned in a lab, you have to pay attention that this pump down phase is fast enough to avoid intermediate melting of the sample before the sublimation curve is reached. Eventually, when the sublimation curve is reached, the phase transition starts, so vapor is generated out of the solidly frozen sample inside of the sample flask. Through the temperature gradient in the system, as the condenser is on extremely low temperature, there will be a pull guiding the generated vapor towards the condenser. And inside of the condenser, the process is actually reversed. So the water vapor, again, through the sublimation curve, will be back transitioned into solid ice, and it will build up around the condenser coil. This is called resublimation. And in an optimal process, sublimation on the sample side and resublimation on the condenser side are in 100% equilibrium. If you achieve this equilibrium, you will have a most efficient process and also the best product yield. Now, during the process, you have to pay attention that you don't overload your condenser. Because as ice is building up on the condenser coil, the condenser will lose efficiency, as the ice itself acts as an insulator and it limits the heat transition between vapor and condenser coil. So once your condenser is loaded with ice, it is time to shut down the system and to defrost and clean it. When you do so, you have to ensure to isolate the pump so the pump does not catch excessive liquid water or moisture from re-evaporated water. So defrost the condenser, the water will drain down into the basin, and from there release it through the drainage of the condenser itself. While doing so, give the pump some additional operation in closed off state and let it clean itself. As mentioned before, in freeze drying, still commonly used are conventional oil-sealed rotary vane pumps. These are available in different sizes and different performance classes to cover the needs of the different types of freeze dryers on the market, starting from small benchtop over pilot scale, floor standing, up to full production scale where multiple units are used. Now, the limitation of these conventional oil-sealed rotary vane pumps is that they're very sensitive when catching excessive moisture and solvent loads, and they tend to corrode or to take, let's say, chemical damage from condensate that builds up inside during operation and that mixes with the oil. Therefore, those conventional rotary vane pumps are relatively service intense. They need a lot of oil changes, they need a lot of service. A much more user-friendly solution is the hybrid alternative, our so-called chemistry hybrid pump RC6. It is actually a good compromise as it combines the performance of a conventional oil-sealed rotary vane pump with a fully chemical resistant diaphragm pump system. What you see here on the picture is, on the left side, a standard conventional rotary vane pump unit. And on the right hand side, there's a chemical resistant diaphragm pump. And this chemical resistant diaphragm pump is attached to the oil chamber of the rotary vane pump. And this brings certain benefits. On one hand, we lower the pressure inside of the oil chamber through the vacuum generated by the diaphragm pump. And this avoids, for most common solvents, as water or other organic solvents, it avoids the possibility of condensation inside of the oil unit. Secondly, the diaphragm pump also creates suction on the oil chamber, so it actively removes the vapor load out of the oil-sealed system, so it keeps it clean. And by applying this permanent vacuum and suction on the oil chamber, during operation, the oil is constantly being degassed. And the result is a system that has largely extended oil lifetime cycles. So compared to a standard rotary vane pump, you may need up to 90% less oil changes. And it is much more resistant when handling chemical loads by means of organic solvents that are commonly handled in freeze drying systems. So this is a very good alternative and a very user-friendly alternative to conventional rotary vane pumps. Now, in some processes, specifically when we look on the pharma and biotech side, the ultimate process purity and cleanliness is required. And this can be achieved only with systems that do not involve any oil, as oil is always a potential contamination source. And on the other hand, there should be systems that do not generate other contamination sources as particles from abrasion. And there the ultimate solution is our VacuPure 10C. This is a screw type pump that is fully dry running, oil free, and through its contact free operating principle, it does not require any sealing components or driving liquids. And therefore it works absolutely dry, absolutely contamination free, adding a high chemical resistance. And if you come to the point where it catches excessive vapor loads, it has a built-in regeneration mode that allows the pump to dry and clean itself within not more than 1 hour, and it's back to full operation as specified. So this is really the optimal solution whenever it comes to the research or small-scale production area on the pharma side, CRO, API production and research, as well as biotechnology. So let me summarize a few of the points that we have looked through. Freeze drying is used to dry heat-sensitive goods and to preserve molecular structure and, as such, the pharmacological functionality of samples. The ideal process combines sublimation and resublimation in absolute equilibrium. The vacuum pump attached to the freeze dryer serves as process pump. It's there for only two purposes. Initially, to achieve the fast pump down, to achieve the sublimation process itself. And from there on, just keep the process condition stable. The actual vapor load is handled by the condenser. For freeze drying, always fine vacuum technology is required in order to achieve the required pressure values below the triple point. And nowadays trend is clearly towards dry running technologies such as the VacuPure for maximum process and product purity. For more information, we invite you to visit our website, where you will find our so-called vacuum pump selection guide, which is an application guidance that will ask you a few questions on the size of your system and what you're intending to do. There's 4 to 5 key questions on different application, and it will guide you towards the proper product solutions. And of course, we are always there for you also on the personal side. If you have specific questions, you can look up your corresponding contact at VacuBrand, and we'll be happy to assist you. So thank you very much for now from my side, and now I'm looking forward to any questions that may have been raised.
Thank you, Carsten. We indeed got a question about the sublimation phase. Is there any equation for the prediction of the sublimation rate?
There's no real equation as such, but of course there are different factors that affect the sublimation rate. And one of them, of course, is the right process condition. So you have to ensure to work with the right pressure condition in order to achieve the sublimation. Try to move in a safe area that is far enough from the triple point, but don't move too far from the triple point, because this will have an effect on your process efficiency. And ensure to have a proper condenser depending on your drying media. A -55 condenser is totally fine with water, if you handle organic solvents or even traces of organic solvents in water, a -85 may be required in order to have sufficient resublimation. And again, if you have sufficient resublimation, this will also cause sufficient sublimation. And if you have your system under control and your process runs perfect, then the main factor for influencing the sublimation rate is the sample surface. So of course, the larger the surface, the more sublimation you can achieve. So these are the factors that you can play with, but at the end of the day, once your system is perfectly laid out to your sample and trying media, then the main factor you can influence is the surface of the frozen sample. So if you run in flask, if you run samples in flask, make sure not to have a very thick layer on the bottom of the flask, but to distribute it over the surface of the internal surface of the flask as much as possible, or to even further increase the surface area, you could consider moving to shelf systems. And there the guideline is very easy. The larger the surface, the higher the sublimation rate.
Thank you, Carsten. We have a couple more questions. How much time is approximately needed to freeze dry a 5-gram ice cube?
Oh, that's a good question. Maybe we should try it sometime. We can definitely have a look into that, make a few calculations. Also there, it depends whether you talk really about an ice cube, which will take relatively long. I would say probably a day, maybe a little bit more than a day, as the layer of an ice cube is relatively thick compared to the overall surface. But if you talk about the amount of ice reflected by an ice cube and it is spread out over a larger area, then of course it would be possible to try 5 grams within a few hours.
We did indeed, for one of the experiments, I think it might be available on YouTube, melt an ice cube, or not melt, but supplement an ice cube. And we did it time bound on that one. And it took us the whole day to record it. So it's really a long-lasting process.
Next time, melt it, spread out the surface, freeze it again, and it will be much faster.
Yep. There is one more question. What is the consequence if the condenser is overloaded because maybe of too low pressure thawing of the sample?
Boiling of the sample?
Nope. Thawing?
Okay. Well, once your condenser is overloaded, that means your cooling coil in the condenser is covered with ice. Ice acts as an insulator, so it basically avoids further heat exchange from the vapor to the cooling coil. And therefore, the efficiency of the resublimation will go down, meaning there will be less resublimation. And this will have two effects. On one hand, you will not capture the full amount of vapor in your condenser, but excessive loads will travel towards the pump, as the pump is still running openly connected to the system. And secondly, when your rate of resublimation drops down because of an overloaded condenser, it will also affect your sublimation rate on the sample side, and your processes will take longer. If you keep further overloading your condenser, you may even come to a point where your process does not work efficiently at all anymore. This is simply the insulation effect of ice on the condenser coil.
Carsten, Does VacuPure comply with CFR 21?
This we would have to check in the background, but we'll take a note and we'll look it up.
Why do we use a 10 times power -3 millibar vacuum pump if we work at 0.01 millibar or less vacuum, since water vapor produced is more when increasing vacuum?
That is a fair question. Well, whenever you work with vacuum in a process system, you have to look at the characteristics of vacuum pumps. And for all vacuum pumps, they have their key specifications, which is the so-called ultimate vacuum, that is the best vacuum that the pump can achieve. And there's the maximum pumping speed, which is the maximum flow that the pump can carry, usually at or around atmospheric pressure. These are, let's say, the limits of the limitations of the pump. But the more important question is, how does the pump behave in between? How does it behave starting from atmospheric pressure with maximum pumping speed towards its ultimate vacuum? And you will find for all vacuum pumps that the pumping performance drops down towards the ultimate vacuum. So in order to run a process, you have to consider that the pump needs to have a sufficient effective pumping capacity at your process pressure in order to run a successful process. So you need to build in some tolerance between the final vacuum and the actual process vacuum. Now you could say, okay, I can use a pump that is in its final performance lower than my actual process pressure, but it doesn't have to be exactly 10 to the power of -3. If you have a pump like the VacuPure that is rated 5 times 10 to the power of -3, that is still fine, but you need some spare tolerance at the low end. And secondly, what you should not underestimate is that while the freeze-drying process is running, the pump in its role as process pump has to keep your process conditions stable. And to do so, it has to cover all potential leakage of your system. And for freeze dryers, specifically for maybe a little bit older systems, eventually at some stage some seals will start slightly leaking. And this is all load that the pump has to compensate. And to do so, it needs pumping speed, it needs suction capacity. And with this background, there's never a 100% leak-tight system. Wherever you have connections, and in freeze dryers, specifically freeze dryers with manifolds, you will find multiple connections that are involved with the system. They all generate some potential leakage, and this has to be compensated by the pump, and therefore you need the effective suction power of the pump, which is only there at the low end towards the final vacuum, but not exactly at its ultimate vacuum, where by definition the flow rate of the pump has to be or is 0.
Okay, we have a complicated question here for a not chemical person. We often face the problem of thawing acetonite water mixtures up to 50% ACN of tone. So optimizing this problem would be looking at the right vacuum to not produce too much vapor or to reduce the condenser temperature. Am I on the right train of thought here?
With the condenser temperature, definitely, because as you mentioned, there's solvents involved. So I strongly assume that a -55 degree centigrade system would not work. A -85 is, we would have to look into the specific chemical characteristics of the mixture mentioned, but I assume a -85 would be the least to look into, maybe even a -100 system. And from the pressure side, if you talk about thawing that you see already in the system, it would be more moving lower in the pressure than moving higher. That will bring you more on the safe side.
Thank you. We have a last question. What is the limiting factor to reducing the time needed for the startup 30-minute phase of the pump or condenser?
Well, the limiting factor by means of the startup time, on the condenser side, it's simply the time required until the specified final temperature, minus 55, minus 85, minus 100, is achieved, which you will see on the display. And on the pump side, all pumps, no matter whether it's a conventional rotary vane pump, whether it's the hybrid pump, whether it's the vacuum pure, they require a certain warm-up time in order to achieve appropriate operating temperature. For oil-driven systems, like the conventional rotary vane pumps, like the hybrid pump, this is a matter of the internal oil temperature that is achieved through the initial operation. And only you will find an internal temperature in a system like this in the range of approximately 70 degrees. Only at this temperature range, the oil has its optimal characteristics for the sealing and the lubrication inside of the system, so it makes the pump ready to take loads. Secondly, at this elevated temperature, the pump itself is much less sensitive to condensable vapors, as the elevated temperature will help to avoid condensation or to minimize condensation inside of the system. For the vacuum pure, as an oil-free but also contact-free system, it requires a certain operating temperature to achieve its full performance. The vacuum pure 10C is based on the screw pump principle, which is a gap-sealed pump technology, meaning there's no active sealing inside, but rotor and stator, they rotate against each other, contact-free, and the performance of the pump is guided by the gap between the moving parts inside of the pump. And only at operating temperature, these gaps are exactly in the range that are required to achieve the full performance of the pump. And this you will simply see when you put a gauge on a pump like that and you measure the performance, that over the first several minutes the vacuum will simply not go down into the range that you need, but after 15-20 minutes it will start moving towards the fine vacuum and finally achieve its full 10 to the power of minus 3 millibar vacuum power. So it's simply a matter of ensuring the performance of the system.
Thank you, Carsten. I think you have answered all the questions. Thanks everybody for joining today. I hope you all enjoyed the webinar and we could answer your questions. As part of the service, we will provide a recording afterwards via email to you. Give us a few days to cut the recording, but latest by beginning of next week, we will send you a link where you can review the webinar again or share it with your colleagues. Thanks again. Have a great day, a great afternoon, great evening, wherever you are.
Thank you. Thank you also from my side, and looking forward to seeing you again sometime. Goodbye.